Okay. Good afternoon, everybody. A very big welcome to our seminar series this term, led by the Centre for Climate Repair. I'm Sean Fitzgerald. We're going to be having 4 seminars this term covering a range of different topics. And I hope that there is something there that will appeal to you. This is a general introduction today. So we're going to be first of all, hearing from Deputy Director Professor Hugh Hunt about the need for climate repair. I will then give a little bit more detail as to some of the areas that we're looking at to try and tease you and get you interested. And then we're going to have one of our 4th year project students, Elizabeth Franks, who's going to be telling us about some of the work that she's been doing over the last few months on a particular droplet generation technique with marine cloud brightening. So I'm now going to hand over to Hugh.
Great, thank you, Sean. The purpose of these sessions here is, hopefully there'll be quite a lot of engineering students here. So just a show of hands, who second year engineering students? Oh, look at that. Now the reason why there's so many of them is because I've just been lecturing them here in the Constance Tipper Theatre, and I told them to walk out of the lecture theatre and turn left, and here they are. Our first year students? See, yesterday I told them to be here too, that's very good. Third year students? Look at that. Any 4th year students? Very good. Oh yeah, you're here because you're 4th year. Graduate students? Very good. And other visitors. And members of our team. Oh, look at this. So we've got a wide range of people here. What I'm quite keen on is anybody who's interested in pursuing PhDs or 4th year projects or summer internships. You know, this is quite a good way of finding out what we do. And come along to these various presentations along the way. And our big thing is about how can we refreeze the Arctic. And the Centre for Climate Repair is pretty interested in not just the sort of technologies to refreeze the Arctic. We have, number 1 on our missions is the first of 3 Rs, deep and rapid emissions reductions. We know we've got to do that. That's just a given. And we've also got to do another R, which is removal of greenhouse gases, carbon dioxide, methane, nitrous oxide, CFCs, other things. But the thing that exercises us the most is refreezing. How do we turn around the melting of the Arctic? Now, the Arctic is warming up. This is from NASA. It's a picture of the globe 100 years ago. And the color code is kind of given on the left. In blue is cooler than average and red is warmer than average. And the average is from some point in the middle of last century. But this was 20 years ago, and you can see things have warmed up, we know that. But the Arctic is looking warmer. And this is where we are more or less now, and the Arctic is hot. There is this thing called Arctic amplification, where the Arctic is warming maybe 3 times faster than the rest of the planet. And that's of concern, because what melting of Arctic ice causes, if there's less ice, there's less reflectivity. Albedo is the word for that. And the reflectivity drops from, say, 0.6 to 0.1 if you've just got open ocean. We really want to keep the ice, the Arctic, reflective. Underneath the ice is frozen ground. And the frozen ground is a lot of vegetation which got frozen in before the last ice age. And now as things are melting, that vegetation is rotting and producing various greenhouse gases, carbon dioxide, methane. We don't really know how bad the methane problem might be, but we're worried about it. And we know that Greenland ice shelf is melting, and we know that that ice shelf holds, if it all melts, which is not going to happen that soon, but there's 7 meters of sea level rise locked up in that Greenland ice shelf, and already the Greenland ice shelf has been responsible for several centimeters of sea level rise. And we don't want that to carry on. And we've seen the impacts of the warming Arctic in the way it has changed the weather patterns. There's been snow on the beaches in Florida, I gather, in the last few days. There's wacky weather going on. Now, if you picture the scale of the problem, the time scale of the problem, I like to think of your gin and tonic or your diet lemonade or whatever it might be, and you've got some ice in it. At what point would you say to your host, hey, can I have some more ice, please? I like this as a visual aid to think, you know what? If that was my gin and tonic, I really would like another block of ice. Unfortunately, we can't just go and order more blocks of ice in the Arctic as much as we'd like to. But now that goes up to 2021. If I take more recent data and I plot that out, I find it's quite helpful to plot it out this way, just because the blue line on the top is how much floating sea ice there is at its maximum extent in the winter, which has all been measured. And then this is the volume of sea ice. Then the red line at the bottom is the minimum. Now, what you saw on the little video just now was the red one. There's another little line which is how much melt occurs. And if the melt is equal to the amount of ice, then when they cross over, we don't have any sea ice. Now, for me, there's less noise on the blue and the black lines, and they kind of intersect sometime in the near future. Now, my kids won't care if it's 2029 or 2036 or 2041. It will have been on our watch. So don't pin me down on that 2029 figure. If it doesn't vanish in 2029, you'll tell me that I'm a climate crank. That's a bit of a problem when you make predictions. But it's going to happen soon. Last year was very warm. This is months along the bottom. I think there's a way of turning that front light off. But anyway, let's leave that for now. That's months along the bottom in each year, and these are the different decades. Last year was hot, the global heat streak. Now, one of the possible explanations for this is that in 2020, it was decided to get rid of sulfur in shipping fuel, bunker fuel as it's called. And sulfur, it turns out, as it comes out of the funnels of the ships, is pretty good at nucleating clouds. And you can see in these satellite images of what are called ship tracks. And they are caused by the sulfur emission of ships. Once the sulfur was taken out, this is a graph showing thousands of tons worth of sulfur. Well, the speculation, James Hansen, whose picture is up on the right, is pretty clear that getting rid of the sulfur has made a big difference. So one of the talks we're going to have in a couple of weeks' time in this same room, 1 o'clock on Thursday, the 13th of February, is could we, human beings, do something about making clouds more reflective? And that's one of the big things that we do in our Centre for Climate Repair. Actually, I might just, so who is students here actively working on something to do with cloud brightening? So we've got 4 or 5 people here in the room who are actively doing research in this area. It's a serious thing. You're most welcome to stick around at the end of today or in future talks and have a chat to them and see if something you might be interested in thinking about. So we're generating lots of CO2, and my concern is that we're being told that emissions reductions is going to do the job for us. We can turn the curve. But if you look at this picture here, which shows the amount of CO2 in billions of tons, this is not small numbers, billions of tons of CO2 that we've been emitting, well, you know, all sorts of crises haven't slowed those emissions down. If we think about the numbers, 40 billion tons a year, the world population is 8 billion, and the billions nicely cancel, so 40 divided by 8 is 5 tons of CO2 per person, and that's an average. Most of us in the room here are probably above average. I reckon I probably got a a carbon footprint of maybe 40 tonnes a year because of flying mostly. But if we think about the things that we actually pay people money to get rid of, we pay people money to get rid of our garbage, we paid for people to take away our sewage. I get fines if my dog was a poo on the, certainly, well, outside Kings, they probably wouldn't mind, they're a pretty liberal sort of lot. But if we think about those, the masses, the weight of these things, this is kilograms, not tonnes. Would we ever get fined for releasing 5 tonnes of CO2? Unfortunately not. So we've got to go down to hit some kind of target in the future. The Paris Agreement is a bit, we've got to be net zero by 2050. Huh? Okay. But there's this word geoengineering, climate repair, what do you want to call it? Climate engineering. There's lots of words you might use for it. Now, it's been on the cards for quite a while. This is a guy, John Shepherd, who sadly died a decade or so ago, but he had this great idea of a thing called the napkin diagram. And I was at the COP meeting in Baku just before Christmas, and I thought, I want to show people the napkin diagram. So I've got my own napkin diagram here, and I'm going to tell you about it. The idea about the napkin diagram is its simplicity. The fact that you can go into a pub or a cafe and you can draw it out. Not complicated. We've got time along the bottom axis here. The next couple of 100 years, who knows. And this is where we are now, 1.5 degrees warmer than pre-industrial. And we know that if we do business as usual, that's what this means, BAU, temperature is going to keep rising, and if we go up, who knows what the numbers are on this vertical axis, but if they get warmer and warmer, that's bad. Emissions reductions, well, emissions reductions are taking a long time. And if we just rely on emissions reductions, there are forecasts that we're going to be 3 or 4 or 5 degrees warmer in the next 50, 100 years. That's not going to work well for us. So we want to do net zero carbon dioxide removal, lots of technologies for that. And the faster we can do that, the better. That means eventually in the future, we will get back down to our 1.5. But in the meantime, this is solar radiation management, and that's what our third strand in Centre for Climate Repair is. So we've got carbon dioxide removal, which also includes methane and other things, emissions reductions, solar radiation management. We need all 3 of them. We can't just say just one of them is good enough. Emissions reductions alone, not good enough. Carbon dioxide removal alone, not good enough.
Make up your mind here.
There we go. If we take it out and put it back in again, how about? Oh! What'd you do? Fine, excellent. The napkin, really rather curiously, if you go onto Google and type in napkin diagram, this is what comes up. Well, not this exact napkin diagram, but it's really weird. You wouldn't have thought, but there you go. So are we going to, It's not moving. Weird.
Maybe press escape. Maybe press escape, come out of the presentation and go back into it again. Oh, they've ruined it.
Okay, I will just come out of that. Apologies. Technology, can't see my mouse is gone. There it is. Right, let me just go out of that and Geoengineering then is climate repair. There's kind of two big strands. One is removing carbon dioxide, this purplish stuff, removing methane, removing greenhouse gases. And the other, the brownish, the gold, I think is a better name, altering the Earth's radiation balance. And in climate repair, we're doing quite a bit in removing methane, quite a bit in understanding ocean fertilization, and we are doing a lot on the Earth's radiation imbalance. So let's have a look at that. The sun's rays come in, the reflectivity of clouds that I mentioned before, that's kind of a really interesting one, a big one. There is reflectivity of high altitude clouds, cirrus cloud thinning. There are a lot of three-letter acronyms. Cirrus cloud thinning, that's the number 5. Marine cloud brightening, number 2. Surface albedo is about reflecting a sun off ice in the Arctic. Stratospheric aerosol injection, that's a very interesting one. Space-based methods. We're keeping an eye on that. I mean, Elon Musk, I'm sure, will be selling us that technology before too long. But some stuff that I worked on 10 or 15 years ago, this SPICE project, which was noticing that Mount Pinatubo, when it erupted, caused a cooling of a degree or so over a year. And we were looking at, could we put stuff up into the stratosphere to reflect sunlight, stratospheric aerosol injection. The only problem was that it was a bit controversial, and for the last 10 years or so, there's not been much work at all on this. What we're really interested in now in our Centre for Climate Repair is re-energising this work, but really keeping on top of the ethics and governance and public perception of this type of work. It's really important that if you're going to do stuff and the public is with you, then getting messaging across is pretty important. So I've told you a bit about marine cloud brightening. Interestingly, there's a whole bunch of people in Australia trying to use this technique to cool the waters around the Great Barrier Reef to stop the reef from bleaching and killing off the coral. If you want to find out more about that, there is a fantastic little video on Facebook, which you can find if you look up. In fact, just put in the three-letter acronyms, MCB, GBR, Great Barrier Reef, and SCU, Southern Cross University, and it gets you straight there. But that's the power of three-letter acronyms. Ice thickening. We've got a big program of this going on at the moment, but you will find out more about that if you come along to our third seminar in 4 weeks' time here on the 27th of February. Other stuff that we're really interested in is this wacky idea of can we anchor a curtain on the sea floor near glaciers. Glaciers are melting. Now this might seem completely wacky. It is completely wacky. Oops. But it's, wow, if it could be made to work, it could really help to control the melting of glaciers. So I'm going just to give a little plug for our Arctic Repair Conference, which is happening in June, 26th to the 28th of June here in Cambridge. There are going to be lots of people coming to Cambridge from around the world. It'll be a fantastic time to interact. We're looking for student volunteers. If you're interested, then send us an email, talk to us afterwards. So if you're around over that period, the student volunteers will be helping to show people around Cambridge, buying them drinks at the pub. No, they'll buy you the drinks, that's for sure. So please, if you're interested, let us know. The program is soon to be published, and you'll find that on our website. Now, there's a lot of stuff on our agenda on greenhouse gas removal. But I'm going to hand over to Sean because this is his domain. So, over to you, Sean.
Just make one point that sort of rather emphasises one of the things that you said. Is that okay?
Yeah, go for it. Yeah, go. Hold on, we're gonna just hold that 'cause it's
Okay, especially
just down there is fine. Yeah?
okay. Especially the first year students might find this of interest. About 10 years ago, I had a really quite high-powered government group come to visit me to talk about climate change. And I showed about the third or fourth picture that Hugh showed, which was how the Arctic was really warming much more than the rest of the Earth, and that was a problem. And the leader of this high-level government commission put his hand up, stopped me and said, hey, that graph, it's not uniform, the temperature rise. And I said, no. And he said, my God, I never realized that. Gee, I'll have to tell some of my colleagues. I know what I thought, and I won't repeat it, but I said to him, yeah, that would be quite useful.
Yeah, getting messages across is important. Sean, over to you.
So, you will hear a bit more about greenhouse gas removal later on in the term, but one of the things that we do here in the department, we are the Department of Engineering, and therefore we like to be numerate. We like to think about actually what is scalable. And there are plenty of people, and we do applaud the efforts. So, for example, nature-based solutions to greenhouse gas removal, growing trees. I'm just hoping that if there are certain numbers that you remember today, the one that Hugh said, like 40 billion tons of carbon dioxide being emitted per year, go and do a little bit of research and find out how many trees you need to get in addition to those which we already have. And then you're going to start wrestling with the issues of where's the land for these trees, and actually what the pressures are on land for feeding 8 billion people and other things like that. So one of the areas that we are really interested in is thinking about the different approaches to greenhouse gas removal that are really, really scalable. And actually quite a lot of our effort, therefore, is focused on the ocean. And one of the challenges with the ocean is that it's a bit like hallowed ground. All right? In other words, you start affecting the ocean. You've seen the programs with David Attenborough and things like that. You have to be incredibly careful for good reasons. But it's 70% of the Earth's surface. The amount of carbon already stored in the ocean is vast. And therefore, the amount of increase that you're looking for uptake, these are small percentages. So, I used to be in the management consulting business. And there was this phrase, if you want something doing, ask a busy person. So go and actually look for where stuff's already happening at scale and seeing actually what are we not doing right for this. And what we are looking at are processes and things that we as humankind have done to the oceans, which have actually reduced their ability to take up carbon dioxide, and maybe addressing some of those actions to allow actually a natural sink to function more effectively. So we're looking at different sorts of ideas in the ocean, and that most of the work is being led by Professor John Taylor in the Department of Applied Mathematics, which is a modelling group, but working with many, many groups around the world. And I'll give you a flavour for those later on. So that's the first area of greenhouse gas removal. Greenhouse gases in the atmosphere. How important is carbon dioxide? It's the thing that we talk about. However, what about this? What about something else that we don't talk about? This is like the biggest secret hiding in plain sight. And that's methane. So methane, as a greenhouse gas, is broadly speaking 200 times more dilute than carbon dioxide. So if you thought carbon dioxide was fairly dilute, let's call it round numbers, 400 parts per million. Methane is about 2. It's actually 1.8. So it's 200 times more dilute. The kick is it's about 100 times more potent for a given molecule. And therefore the ratio of its importance to warming today is about 1 to 2. So it's actually responsible for about a third of warming today. And therefore, some of the work that we're doing here in the Department of Engineering is looking at sorts of materials that we might be able to do to accelerate the oxidation of methane and convert it to carbon dioxide, which is itself a greenhouse gas. But put it like this. Look at the increase in carbon dioxide per year that we are already experiencing. And it's about 2 parts per million per year. So if you were to convert all of the methane magically today in the atmosphere to carbon dioxide, you would increase carbon dioxide levels by about a year's growth. But you would reduce the warming, right, based on this by, we'd lose that third. So it's got a huge potential. And the sorts of things that we are looking at are development of catalysts just to try and get the methane to be converted on its journey from methane to carbon dioxide. We know energetically that's what it wants to do, otherwise we wouldn't be using it for energy production. But it needs to get over an energy hump. And when the methane is sufficiently concentrated, then the heat released by that is enough to get the next molecules to go and convert as well. But when it's so dilute, that's the problem. So that's why it hangs around. It's got about a half-life of about 10 years. And we're looking at the development of electro and photocatalysts. So it's in the lab, in the English building, and they're doing sort of development of what you might add to things like titanium dioxide, what kinds of metal nanoparticles. So it's the nanotechnology groups over here in the English building that are looking at this. And where might you go? Where might you go in terms of applying these sorts of things? One of the big problems we've got with carbon dioxide right now is that we need carbon markets and things like this. So it's not just technical, you've got all of the business problems behind this. So what we're interested in doing is trying to find opportunities that where these catalysts could not just be sold as a carbon dioxide equivalent, sort of good for the climate. What other benefits might actually these catalysts provide that people will pay for here and now? So the first thing we're looking at is looking at electrocatalysts, photocatalysts on the surfaces of buildings. The Shard, which is actually a building I did work on, covered in huge amounts of glass. I wouldn't fancy being the window cleaner, all right? But therefore, actually, what kinds of coatings can you put on the glass that are then self-cleaning? Those coatings, what do they currently use? Titanium dioxide. Titanium dioxide is a potential catalyst, photocatalyst. Well, it is a photocatalyst, but we're looking at what we might be able to do to enhance it. So getting more of these buildings to use these sorts of opportunities. So that's the realm of photocatalysts. And then what about the role of ventilation systems? So we've got a postdoc called Samuel Tomlinson who's done some work recently. It's going to be published hopefully fairly soon. But what he's identified is that where air needs to come into contact with a physical surface, that's when the catalysts can start to work. We've scoured using engineering analysis, looking at the amount of air that comes into contact with planes, trains, automobiles, buildings, the surfaces. And the biggest opportunity that we think that we've stumbled upon is actually the air that moves through a ventilation duct. This is mechanical ventilation systems. And it's not the walls of the duct, okay? Because if you're a semi-decent ventilation engineer, you're going to build a nice big duct to reduce the resistance of the flow, which means the air does not come into contact with the surfaces. But where does it come into the contact with the surfaces? And they're called HEPA filters. And we put filters in ducts for another reason. We can put filters in ducts to go and trap viruses. Oh, shoot, yes, of course, it's called COVID. So it's even more exciting about getting filters into buildings these days. But filters are very good at trapping particles, solid things. What about the gases? And if you're in the buildings area, you'll get interested about sort of the furniture, paints, things like that release volatile organic compounds. So some of the more gaseous materials. Actually, can we develop this catalyst so that it won't just knock out methane, but it will also knock out some of these volatile organic compounds? And then people would pay for these catalysts on those filters for health benefits now, and the climate's then a co-beneficiary. So that's kind of some of the work that we're doing here at the engineering department. And then lastly, I wanted to just share with you, we're not just thinking about physical sciences, physical sciences and technology, we're looking at the social sciences, so the acceptability of these. And if you're interested, there's some work that was done, published in iScience, looking at public attitudes towards things like geoengineering. I was a bit surprised. We did a study of 13 years of Twitter data, and it was rather more favourable than I was expecting. I was expecting it to be just full of red, we don't like this stuff. So that was an interesting first piece of analysis that we uncovered. And then when Ramit, who undertook this work, I said, well, this is really interesting. And I said, Ramit, what else are these people talking about? So it's 13 years of Twitter data. This is before Elon Musk took over, because you can't access the data now. But so it was earlier than that. Oh my goodness me, what did we stumble upon? What else are these people talking about? We then uncovered that the same voices, so in terms of on Twitter, are those who are also talking about Trump, MAGA, anti-vaxxers, chemtrails, you name it, conspiracy theories. So we wanted to make sure that people were alerted to the wider conversations that are going on with the same groups of people who are active on things like Twitter. And to the extent that this conversation made it into Time magazine, because actually it was about conspiracy theories, and all we wanted to do was to share this information, because it might just influence, inform what level of credence you then want to ascribe to any commentary on things like geoengineering. So I wanted to say thanks to a huge number of people here in Cambridge. So it's a growing centre for climate repair across many, many departments, involving the academic staff, postdocs, PhDs, engineering students in their fourth year, and summer interns. So it's a growing activity here in Cambridge, and with collaborations in many, many institutions, not just here in the UK, but around the world.
So now we've got, the idea is we've got some time now for discussion, for any questions you might have, any concerns you might have. I mean, I've been very concerned over the years at just how we can have discussions in a room like this, and you generally get the impression that, oh wow, this is really interesting. Oh, good, let's keep on researching this stuff. But then when you start reading newspapers, it's all very negative, and that's the world we're in. So we're interested in any comments you might have. We've got a second microphone, I think. So,
It's not only reading newspapers.
Can we just get other people to speak there just for a second? Yeah, that'd be good. Yeah.
I was just going to ask, what causes Arctic acceleration?
Sorry, what?
What causes Arctic acceleration?
What causes Arctic? The Arctic Arctic amplification. It's a very interesting phenomenon. If you look up Arctic amplification, it's complicated. But one of the things that you've got to recognise is that if you think hot air rises around in the equatorial regions, and in the polar regions, the cold, and you get, so there's a circulation that the Earth is rotating, and you've got the circulation, you've got lots of Coriolis forces coming into play. This is why you get the high pressure systems rotate in the opposite direction in the northern hemisphere than in the southern hemisphere. But the energy, the heat energy, is being concentrated into a smaller place. So that is one cause of Arctic amplification. There are other causes, which is to do with the oceans warming up. We've got warmer oceans, and that warm water is being channeled up into the Arctic regions. There are many other effects going on at the same time, but the worrying thing is that it's happening, and it's going to be quite hard to slow down that amplification, because all the effects I've just talked about are quite hard to change. So we've got to try and find some way to reverse the melting of the Arctic. There was another question. Why don't you? Yeah. Well, it's because we are recording it, so I think it's it.
So I saw in your collaborators, you had some collaborators in California and in the US. And in the wake of Trump being elected as president, how do you think science such as this might change?
Well, why don't you have a go at that one, Sean?
No, you. So, that's a really good question. We don't know, but we are expecting change. So, I think one of the things we've learned is that with the change of administration, things can be a little unpredictable. That's a very British way of saying it could be very unpredictable. So, we are expecting changes. And in fact, I think maybe later today is what we're expecting. There may be an article in The Conversation on this very topic. So look out for that.
I mean, I kind of think that Trump could get quite excited about geoengineering, and could. it could try to own it as his thing. Oh, no one's ever heard of this thing before. That could happen. That would be a bit bizarre, but it could happen. He may say, drill, baby, drill, and at the same time instruct the Air Force to spray sulfate aerosols because, that'll help cool things down. I'm going to save the planet. Or he may just completely ignore it. It might just be something he's not interested in. And what we've seen is that if he's not interested in it, then nothing happens. So look, boy, now are there, I don't know, any US citizens in the room want to comment? Or is that, no, that's unfair. Right, other questions? We got a question.
Oh, no.
We got yeah.
Hi, I'm a second year, and I was wondering, if we were interested about these kinds of things, do you have any recommendations on what third-year courses we could take?
So the question is, what third-year modules might you take? Now, I don't know all about the third-year modules because I don't take them. But I think that in general, if you're interested in, say, fluid dynamics, then do what you're interested in, 3A1, 3A3, and so on, because there's plenty of fluid dynamics when it comes to the stuff we're doing in climate repair. But I think it's fair to say that we've got some work going on at the moment in cloud brightening with all sort of COMSOL modelling and droplet generation, and Jake, who's doing quite a lot. Is Jake here? Jake, who's doing quite a lot of that work. What modules did you do? So you're doing quite a lot of fluid mechanics. What modules actually did you do? Any fluid mechanics modules?
So I specialised in electrical engineering, so no, I didn't. So it's been really interesting. Yeah. So I would say if you're interested in working with Centre for Climate Repair as an internship or fourth year, don't worry about your module choice really. A part of it is the whole learning process, and you'll very quickly get up to speed with the relevant topics.
Other questions? We've had one of them. We'll come back in a second. Yeah.
Who was it? Yeah. Awesome. With the cloud brightening and droplet generation and those technologies, are we also doing research into the effects they could have on other climate processes? Like one that comes to mind is maybe the monsoon in South Asia. Is that something we're concerned about?
Yeah. Well, so William, do you want to say something about that? So William's doing a PhD on cloud physics.
Yeah, modelling of marine cloud brightening. So basically that really depends on where in the world you do it. So different parts of the world are connected to other parts of the world through various kind of atmospheric processes. So that part of the research is understanding how those parts are connected. So one example is if you do marine cloud brightening off the coast of West Africa, sorry. Cooling the sea surface temperatures there will reduce rain in the Amazon and then can dry out the Amazon. So yeah, that is an area of research that you have to kind of do global modelling for. So my PhD isn't focused on global modelling, but that's something that other people are doing.
And it's rather curious that the marine cloud brightening research going on in Australia and the Great Barrier Reef, it turns out that if you had to do marine cloud brightening anywhere in the world, that's possibly the worst place to do it because there's hardly any moisture in the clouds. Beautiful blue skies. I'm not an Australian Tourist Board member here, but you get the idea. So what they're probably doing with their boats in Australia is producing a low-lying fog rather than anything to do with clouds. But boy, it's a big question. How do clouds work, and what impacts would what we're doing have in regions other than where we're putting in their clouds. The people we work with in TU Delft in the Netherlands are very active in that kind of area as well. So we've got a question here. Yeah.
My question was, what can a first year do to actually help you guys now rather than in 3 years' time?
Really good question. So we do generally offer summer internships. So during the summer, I know that we will be doing that this year, and that's all opportunities for actually students across the university, but some of the work is more relevant for those with an engineering background. So Aliki here in the room is working on the development of catalysts, and actually we are going to be looking at, for example, that's just but one project. The others should be clarified during the course of this term. Next.
Okay, so we've got another
This lady here.
another one over there. So yeah, go on.
So you're doing loads of research into all of these things and it looks pretty positive, but when are you actually going to be able to implement this to be able to have the kind of global change that you're saying that we need? And what are the sort of barriers to you being able to implement this?
So what is very, very important is who pays for this research. Now, if our research was being paid for by ExxonMobil, well, we wouldn't be in existence. We'd be hounded out, because if our research is paid for by Bill Gates, well, would you be content with that? But if our research is paid for by the UK government, then that would feel better. And it turns out that for the first time in 15 years, right now, as we speak, an organisation, UK-funded organisation called ARIA, has put 60 million on the table. And next week we're being interviewed for a few of these projects. If we get funding from the UK government, that, I think, will really accelerate the interest. The number one thing about ARIA is they're funding outdoor experiments, which has never been done before. Outdoor experiments, you get funded by, well, imagine if Elon Musk gave you some money. Would you trust him? Oh, there we go. We're going to have to wind up in a second. We've got one question up there, and then we've got a couple. Okay, let's see how we go. Yes, with that one up there.
Hi. I want to ask, do you think artificial intelligence will play a very important role in the future in solving climate those questions? Because obvious it will help, but do you think it will provide like a brand new solution about it?
I mean, AI, we've already got some AI input in our group. For instance, trying to understand clouds, AI is going to help us with that. Yes, answer, most definitely yes. Have we got time for...
I mean, we have a live PhD looking this right now. Alice Cicciarello in the department applying AI to actually looking at cloud formations and, in fact, where you might target things like marine cloud brightening to minimise the effects and maximise the benefits.
Right. Yeah. Did you want to say? David.
Sure. Thank you. Yeah. So you had the napkin, whatever you call it,
napkin
the demonstration, and that's very clear that you need the emissions reduction. Mm-hmm. And the removal, and the SRM as well. But how widely accepted is that?
Not.
Is it right? But is it accepted at COP? Is it accepted by governments? Because that seems like a huge problem.
It is a huge problem.
Addressing.
And the real thing is that there's a talk which we've got. It's online. You can watch it, where we talked exactly about the napkin diagram at COP. And we hoped it would have a bit of an impact. 10 or 20 people turn up. It's disappointing. And people tell us to stop talking about this because we should not be even thinking about solar radiation management. We've got to focus on the important thing, which is emissions reduction. Well, yeah, look. Yeah, big issue. We've got to wind up. Just two more. We've got Andrew, just a quick comment? Or?
Yeah, sure.
Yeah, there you go.
I was waiting for the mic there. But, Sean was talking about titania and using that in heating systems and stuff like that. But why not have it free floating in the atmosphere so it has either a SRM effect or a marine cloud brightening effect? What's the logic for keeping its beauty concealed in a filter that no one can see it?
Yeah, absolutely. We could do methane catalysis by injecting stuff into the atmosphere. At the moment, we don't really have permissions to be injecting stuff into the atmosphere as geoengineering, whereas putting stuff into air conditioning ducts is something that will be way less controversial. There we go.
Well, can I just make a brief comment in response to the question about Trump? We really don't know what Trump
Further
will...
away from you, Matt. Yeah, that's
So we really don't know what Trump will do, but what I think is worthwhile considering is about 4 months ago, a high government official came to Cambridge and gave a fabulous talk on climate change. Really wonderful. He knew what he was doing. And at the end, because I know him slightly, I went to see him and I said, look, when you were advising Johnson, you must have been even better because you were talking just to him, whereas for us you were talking to the whole group. And his face fell and he said, Johnson doesn't understand a thing about climate or science in general. The minute you start talking science to him, his face just falls, and he said, it's like if I spoke Greek to you. You wouldn't understand a word I'm saying. Trump doesn't know any science either.
Right, we've got to wind up. Look, we're a busy engineering department. There's another lecture here that starts at 2 o'clock. Before we go, please join our mailing list. If you've got the ability to read our QR code. Thank you all so much for coming, and hopefully we'll see you again in a couple of weeks' time. Stick around if you want to chat to some of our students and some of us. Thanks very much.